Very good morning, all of you. After this Faraday's laws, the concept of self-induction and mutual induction, two more important titles we will cover today in this session. One topic will be LC oscillations, and the other topic is motional EMF. Along with it, we have some small trivial topics that also we should try to cover that. LC oscillations. See, let us remember one principle that capacitor, a device which stores energy in the form of electric field, and inductor, the device that stores energy in the form of magnetic field. We have given expressions in yesterday's session. Now let us take the case. Here I have shown a simple circuit where this is a capacitor which is fully charged capacitor connected to an inductor. Now initially there is a key which is open. Now initially what is the condition? Capacitor is fully charged to maximum potential, charge is maximum, and hence the total energy is in the form of electric field. Since key is open, no current through inductor. No current through inductor means, yesterday we have given expression half Li square. No current through inductor means no energy stored in the inductor and hence no magnetic field. Now, if this key is closed, that is, a fully charged capacitor is now discharged through inductor. Now initially when we set T equal to 0, this capacitor starts discharging. When capacitor starts discharging, yes, current through the inductor starts increasing. Discharging of the capacitor when it starts, the current through the inductor starts increasing from 0. Therefore, this discharging process will take place for a while. See, when discharging is happening, what is happening inside the capacitor and what is happening at the inductor? You see, when discharge is happening, the charge in the capacitor is decreasing in gradation, and hence the electric field is also decreasing because energy stored will decrease due to the decrease in the charge. So during discharging, charge due to the capacitor is the decrease in gradation, and hence the energy in the capacitor will decrease and hence the electric field will decrease. This is at capacitor. Now at inductor what happens? During discharging, the current through inductor starts increasing from 0. And once current starts increasing, the magnetic field inside, the energy inside the inductor increases, and hence the magnetic field inside the inductor increases. So discharging, what happens? Electric field decreases, magnetic field increases. Now in the next step what happens? The capacitor starts charging. The capacitor gets charging through inductor, and in this case what happens? The reverse will happen. That is, one more time the charge on the capacitor plates increases from 0 to maximum, and hence once again the electric field increases from 0 to maximum. In such case what happens? So during charging of the capacitor, the current to the inductor is decreasing and hence magnetic field inside the inductor is decreasing. This cycle will repeat. This cycle will repeat such that what we have explained earlier, it causes a oscillation, a fluctuation of electric field and magnetic field in the capacitor and inductor, which is popularly called as LC oscillations. Later, it becomes a big principle for a electronic instrument called as oscillator. So these LC oscillations are now seen as L for inductor, C for capacitor. LC oscillations are nothing but the periodic changes that we are getting in the electric field and magnetic field. Now these fluctuations I have told you, both electric as well as magnetic field fluctuations will be periodic with a certain frequency. Now we are giving some appropriate results, and see, after giving the results I will discuss as a concept which will cover almost like a dozen examples, different types of examples you can say. Now, initially t is equal to 0, the maximum charge on the capacitor is Q maximum is equal to Q naught. Then, while discharging or while charging, I use another one, what is called as the Q term, which is called as instantaneous charge. So look at these symbols, Q for instantaneous charge, Q naught for the maximum charge at t equal to 0, fully charged capacitor. And also one more term we make use is omega, the angular frequency of the periodic fluctuations. This omega is equal to 2 pi times f, where f is the frequency of oscillation, or 2 pi by capital T, the time period of oscillations we can take. Now, let me give that expression. The instantaneous charge Q is equal to Q naught times cos omega t. Remember, here periodic function, when it comes, we can use either sine or cos, but we are taking the case of fully charged capacitor getting discharged. Then the equation of charge is having cosine function. Please take care of this. Q, the instantaneous charge, is equal to Q naught times cos omega t. This is instantaneous charge. Now, I have told whether during charging or discharging there will be current through inductor. So that is why we write current I. Of course, it is nothing but dq by dt, available current, rate of change of flow of charges. So dq by dt will give you as Q naught times omega sine of omega t, sine of omega t. Yes, of course, with negative sign also you will see. That negative sign shows the phase difference between the change of, the change in the charge and the current. So that phase is what is given by this negative sign. This is what we write it as this equation. I is equal to I naught cos omega t, sin omega t, I naught sin of omega t. So two expressions. One for charge, Q is equal to Q naught cos omega t, and if you take the derivative, I will write here for current. The expression for current, it will be I is equal to I naught sin omega t. Now here once again you will find that this is a cos function and this is a sine function. We know that both are complementary. When sine values take maximum values, cos values take minimum values, and vice versa. That is what is that phase difference between the two changes that are happening. Now, as I have told you how to make use of this expression, more and more number of examples. I can definitely say some dozen examples I will show you in a single expression. Look at it as a concept. Now, to begin with, I will take, if capital T is the time period, if capital T is time period, we will write omega is 2 pi by capital T. Right? Now, Q is equal to Q naught by 2, suppose. If Q is equal to Q naught by 2, or else let me take Q is equal to root 3 by 2 times Q naught. Why these values specific? Because generally for CT and NIT, these are the regular numericals that we observe. The same I am now giving you here. For Q is equal to root 3 by 2 Q naught, I will just make one substitution, and for the remaining things, I will just take the result. That is root 3 by 2 Q naught is Q naught times cos of omega 2 pi by capital T into small t. Here you get cos theta is equal to root 3 by 2. Means theta is equal to 30 degrees, that is pi by 6. Therefore, here we get 2 pi by capital T into small t is equal to pi by 6. Theta is equal to 30 degrees, the pi by 6, which will show you that t is equal to t by 12. Right. So t is equal to t by 12 is the required time period for Q becoming root 3 by 2 Q naught. I have shown you one method. Similarly, the other numbers that we are given are, it is half of Q naught, or else 1 by root 2 times Q naught, like that. So for those values I am giving the results. See, the process, please you remember. Don't try to remember the numbers. Even if you forget, this method should give you the answer. Now, what is the P you got? This T is equal to T by 12. Next time, I take Q is equal to 1 by root 2 Q naught. This 1 by root 2 will give 45 degrees cos 45 pi by 4. That substitution will give you small t is equal to T by 8. Small t is equal to T by 8. And one more number is Q is equal to, yes, half of Q naught. Half of Q naught. Half of Q naught. Q is equal to half of Q naught. See, T is equal to, you will get it as a T by 6, and Q is equal to 0, you will get T is equal to T by 4. So for a given time interval, what is the charge? Or for the charge, for the given instantaneous charge, what is the time interval? This becomes one thing. So second one also you see. Charge becoming root 3 by 2 times. In the case of capacitor, the energy stored is given by Q squared by 2C, because here Q is changing, V also changing, and that is why I have taken Q squared by 2C, not CV squared by 2. So when charge is changing, there will be a corresponding change in the energy also. What is the expression that I am using? The expression that I am using is U is equal to Q squared by 2C. In such cases, see, Q becoming root 3 by 2. Q squared becomes 3 by 4. Therefore, at T is equal to T by 12, U is equal to 3 by 4 times U naught. That is, the energy has become 75%, means that 25% of energy is now the other way. It becomes the magnetic energy in the case of inductor. Therefore, UC is equal to 3/4 of U naught. Now what will write? The inductor, the energy will be 1/4 of U naught. 1/4 of U naught. The ratio becomes 3. The ratio of energy stored in capacitor to energy stored in inductor. One more example. If that is equal to 3, what is the time period? So the time period is T by 12. Now here, Q becoming 1 by root 2. Q squared by 2C when you do. This square term will give you 1 by 2. Therefore here, UC is equal to half of U naught and UL is equal to half of U naught. See one more thing. So, what is 50% of energy? 50% of energy in the form of electric field and 50% of energy in the form of magnetic field. The ratio is 1. Which instant? T is equal to T by 8. So any one parameter like charge or time related or time energy related. So such pairs of examples are very popular, and in other cases now you can write on your own. This becomes 1/4 of energy. This becomes 1/4 of energy, and here in the inductor it becomes 75%. And at T is equal to T by 4, where the process of discharging will be stopped and process of charging gets started. So here UC is equal to 0 at this moment and UL equal to U naught. U naught. Now you see, I have told in terms of charge, in terms of energy. Now the same we can also use it for current as well. When a charge is root 3 by 2 times for T is equal to T by 12, capacitor 75% of energy and inductor 1/4 of the energy. Here I will show one more tabular column. Please try to follow that. This is 1/4 of your right. Now what is current in the circuit or current through inductor? Current through inductor. Here you got 1/4. What is the maximum energy, you tell me? Maximum energy is Q naught squared by 2C if it is the energy in the case of capacitor. The same will be half L I naught square, where I naught is the maximum value. Now therefore you can see 1/4 of the energy means take root, you will get 1 by 2. Therefore here current is half of the maximum current. Half of the maximum current, and here the current, instantaneous current through the inductor I am writing is the last row, I is equal to 1 by root 2 times I naught, and here I, the instantaneous current, is equal to, yes, root 3 by 2 I naught, and this is where I is equal to maximum I naught, and this is what is referring to the phase difference. Here you see, while the charging completely gets over, Q on the capacitor is 0 and current through the inductor is maximum. So this is how you find the different possibilities of LC oscillations. The charges, the time intervals, energies, energy, ratios, whatnot. So LC oscillations, an important topic. Follow this and do as a small tabular column work for about 5 to 10 minutes. You will easily expectize the answers in LC oscillations. Now, last but not the least, all important thing, during LC oscillations, the periodic oscillations, what will be expression for the time periods and frequencies, right? That expression is omega is 1 upon root LC. L for inductance and C for capacity, root LC. 1 upon root LC is what is omega. Therefore, whenever you need frequency, F equal to 1 upon 2 pi root LC, and the reciprocal 2 pi root LC will be the time period, like that. So maybe given numbers or as it is symbol. Now supposing here if I have to write T by 12, what is this one T by 12? This is 1 by 12 of what is the value of T I got? T value is, yes, 2 pi root LC, which will get it as, yes, pi root LC by 6, like that. So substitution for T also I have shown. The expression for omega, expression for frequency or time period with this tabular column. See, I am again telling you, very tough examples for most of the students, because the concept of oscillations is also linked with it using sine functions and cos functions, and that is why practice this tabular column once or twice. Yeah. See, one more title, motional EMF. Earlier it was self-induction, mutual induction, and now it is motional EMF. Whatever may be the title, origin is the same. What is that? Faraday's first law, the change of flux giving rise to induced EMF. And the expression for induced EMF is also the same, which is Faraday's second law, which says E is equal to d phi by dt along with the negative sign for sense of direction. Now look at this motional EMF. We are not going into too much of theory part. We will write the expression, and how to make use of that expression will be our discussion. Look here, we have a magnetic field that is represented, and as usual uniform magnetic field represented normal to the plane of drawing, board or your paper. I am telling you, your paper or board, this B bar is normal to the plane, either normally outwards or normally inwards. Here in the figure I have shown normally inwards. Now, TQ is a straight conductor of length L, and it is moved with a velocity V bar such that this L bar and V bar at an angle theta. Remember, when you are writing this, both L bar and V bar are in a plane. 99% of our examples for NEET and CET. Need not be always, but most of the examples that we get are the same. So this theta is the angle between L bar and V bar, and it's a plane angle, both are in the same plane. Now, the very popular expression is the induced EMF. Induced EMF across P and Q, I am telling you, between the ends of the conductor, E is equal to BLV sin theta, which is a kind of scalar form that we have. Simply writing, E is equal to BLV sin theta, and here theta referring to angle between L bar and V bar. In fact, correct form will be a triple product. This is what is V bar dot L bar cross V bar will be a correct expression. That is, whenever we are given all the different orientations about magnetic field, about the orientation of the conductor, and also the velocity, then this is our actually generalized expression. E is equal to B bar dot L bar cross V bar. Order is important, or is the same dot product. I will also write it as L bar dot V bar cross B bar is also the same expression. Both will give you the same. Remember. So this is how we are taking it as a triple product. This gives BLV sin theta expression. Now, here what will be the direction of induced current? Induced EMF giving rise to induced current. What will be the direction? And for the direction we use, yes, right hand rule, Fleming's right hand rule. Fleming's left hand rule earlier, you remember, this was magnetic field and central finger was for current. Then finally we got thumb as the direction of magnetic force. But to find the direction of induced current, this is what is the rule. Again, three fingers placed perpendicular to one another. Index finger again showing the direction of magnetic field, and the thumb shows the direction of motion, that is velocity. Then this central finger shows the direction of induced current. So that is how we have to make use of that. Supposing if I show you in the same example, what will be the direction of induced EMF? Right hand rule, not left hand rule, right? Again, index finger, direction of magnetic field, yes. And supposing if it is moved in this direction, from your left to right, see, from your left to right, then I have to use my thumb. Then look at the central finger is upwards. Therefore, now the current is from P to Q directed. Therefore, this becomes higher potential and the Q end will be at lower potential. That is how we make use of this right hand rule to find direction of induced current. Now, to show one or two simple examples here based on this BLV sin theta, because we need one clarification. Because when we do examples in Earth's pertaining to Earth's magnetic field, conductors, motion, not in other magnetic fields but in the magnetic field of Earth, we know by principle that Earth's magnetic induction has two components. That is horizontal component, which is given by B cos theta, where this theta is the dip, that's what we have the magnetism, and vertical component is equal to B sin theta. Now in which of the examples we use BH and which of the examples we use BV is such a vital case. So for that reason, now I am giving you one or two examples for this clarification. Now look here. Supposing I show this is a kind of railing. This is a railing. And this is a straight conductor. This is a straight conductor. Supposing this length is L. This length is L between these two ends. Now this entire setup is in Earth's magnetic induction, and because of this free fall, what happens? See, as it falls down, the area of this loop gradually increases. Area increasing means flux is increasing. And what is the rule according to Lenz's law? When there is change of magnetic flux, EMF is induced in such a way that this increase in area causes increase in flux. Therefore, the induced EMF tends to decrease the flux. So the consequence of Lenz's law, how we always use, if it is increase in current and increase in flux due to outside agency, the induced current will have the opposite effect, that is to decrease the flux. Vice versa. If the external agency is causing the decrease in current and decrease in flux, the induced current always tends to increase the flux linked with the coil, like that. Now in this case, the area increasing and all flux changes, and therefore, so here when we are writing that what is induced EMF E, we write it as BLV sin theta, of course, where this B we have to take it as the vertical component, because here we have taken the vertical fall of the rod. vertical fall of the rod. Similarly, we are given examples such as wheels of a train rotating and moving in a horizontal track, on a horizontal track. Even in such examples, what are the keywords? Wheels of the train, horizontal track, or else sometimes aeroplane takes off, or aeroplane is landing. In such examples also, the EMF induced across the ends of the wings, keywords, aeroplane, landing, runway, ends of the wings, induced EMF. In all such cases, we have to use BV, vertical component of Earth's induction, not the horizontal component of Earth's induction. You remember that. One more example you see, supposing in this case what happens, because of the free fall velocity gradually increases, but after that the induced current seems opposing of this free fall, because this free fall opposing the increasing area, right? Therefore, this induced current in other way, it is opposing the free fall. Therefore, after a while, there will be two forces. What are those two forces? See, this is E is equal to BLV sin theta, of course B being vertical component, and therefore what is the current? I is equal to, yes, vertical component LV, suppose sin theta is equal to 1, I have taken, by capital R, if capital R is the radius of that loop that we have considered, the total resistance of the loop that we get. Now therefore, according to this expression, F is equal to ILV sin theta comes into picture. F is equal to ILV sin theta comes into picture, which will give rise to I, which is BLV by R times L times B. Let us take sin theta to be 1. So finally this is what is B square L square V by R. This is what is the force, which is the magnetic force due to current in the external magnetic induction. Now, when mg is the force which is causing the sliding downwards, the free fall, when this force opposing that mg, why opposing? Because of the consequence of Lenz's law, then after some time this will acquire a terminal velocity which is a uniform velocity. Therefore, this fall will be with acceleration for a while, and sooner this will acquire a uniform velocity. Why uniform velocity? Because mg is balanced by this force B square L square V by R. Net force becomes 0, acceleration becomes 0, and hence V will be a constant, that is called as a terminal velocity. So in this example, what is the terminal velocity and expression? So B squared L squared V by R is equal to mg. If m is mass of this wire which is falling under gravity, so B square L square V by R equal to mg is one condition. Here this condition can be used for any of the examples, such as expression for B or V or L or M, whatnot. So for any of such things we can make use of this E is equal to BLV sin theta. Now one or two more examples you will see here. The case of a rod rotated in external uniform magnetic field. A rod of length L rotated with a constant velocity omega in an induction of capital B, then this is what is the expression we get. E is equal to half B L squared omega. Half B L squared omega. Remember, whenever we are talking about EMF that is induced, it is always due to the reason of change of flux. And therefore here in this case, important aspect would be the axis of rotation. The axis of rotation. Supposing field is vertically upwards, and considering one such case, suppose magnetic induction is upwards and the axis of rotation is also upward. Axis of rotation is also upward. Axis of rotation upward means, see, this is the rod I have taken and this is how the orientation, and now it is made to rotate in a horizontal plane. Rotations in horizontal planes means Yes, the axis is vertical axis it becomes. Now in this case, whatever rotations we find, we don't find any change of flux. Any change of flux, no. And that is why no question of any induced EMF. So remember, whenever we consider such cases of rod or disc or any other coils rotated in magnetic field, for the cause of induced EMF as a result, we always need, the most important thing is the axis of rotation. Now supposing this is how I have placed and this is how I have rotated. Now here magnetic field is upwards and this so-called axis of rotation is perpendicular to this one. In such case, there will be induced EMF because of the change of flux. Because that sector gradually changes. When sector gradually changes, all those area changes and change of flux, the increase or decrease and whatnot. No, this will cause as a change in flux and magnetic EMF is induced between the ends. Therefore, here the important aspect is regarding axis of rotation. So this E is equal to half B L squared omega. Any of the expressions when we have given, maybe a small change in the data. How? This time he says not the length of the rod. He simply says that a rod with a frequency F or time period capital T rotates such that it describes an area capital A. Then naturally what will be the area swept by this rod? It will be a circle. Therefore, in such case, what is that we need? So A is equal to pi r square becomes pi L square because L the length, and now we are rotating about this end perpendicular, and therefore length of the rod becomes radius of the circle. A is equal to pi L square. Therefore L square is equal to A upon pi. So that is a simple substitution. E is equal to half B, what is L square, A by pi, and omega, as well, supposing if it is given in terms of frequency or it is given in terms of time period, then we write it as 2 pi f or 2 pi by t. So this gives you B A F, or this is what is B A by t, where you will find again different relations and based some numerical examples also. Here E proportional to A, E proportional to 1 by T, E proportional to F, whatnot, all these results. Here in the case you will find E proportional to L square. Once again, the direction of induced current we use, yes, right hand rule, Fleming's right hand rule will be used. Supposing the same example with a difference. What is that? In the case of, instead of this rod, I will change it as, supposing this is a wheel. This is a wheel made up of large number of spokes. A very popular cycle wheel, we know that, made up of large number of spokes. Now, in such case, this is a wheel where L is the length of each spoke. The terms you please look for. L is the length of each spoke, and let me take N as the number of spokes. Then what happens if you consider any two diametrically opposite ends? This is nothing but large number of straight conductors as a parallel combination. Each and every spoke now acting as a voltage source, which gives rise to, yes, E is equal to B L, this one for V. No, already we did it, and what was our answer? Half B L squared omega. This is for each spoke. Now, when we consider all such n spokes, it is nothing but the parallel combination of all EMF sources. And we know that in the parallel combination, potentials never added, it becomes a common potential. Therefore, even for the case of a wheel with n spokes rotated with a angular frequency omega. For that also E is equal to half BL squared omega. In this case also remember E proportional to n power 0 independent of number of spokes. Number of spokes. Similarly, instead of wheel, even you can call it as disc. A disc rotated. Even in such case also we can assume or we can take that the disc is made up of large number of radial elements, each of the radial element acting as a rod. Even for that also you will get the same expression. There instead of L we will also call it as radius, capital R. You will get it as capital or the radius likewise. Now the most important point in these examples is the axis of rotation. Now as a last but not least one topic which is very popular and it becomes the basis for our next chapter. Now a coil rotated in external uniform magnetic field. External uniform magnetic field. Again remember, for such case the most important thing is the orientation of the axis of rotation. We have already mentioned what should be the plane of axis of rotation and what should be the plane of magnetic induction. Now by definition for a coil we have taken phi is equal to NAB cos theta. Cos theta. Why here comes theta? Because when we are rotating a coil at a constant angular velocity, this theta is equal to, yes, omega times p you will get, where omega is the angular frequency. Therefore here theta term I will straight away write it as cos of omega t. And now what will be the induced EMF? Yes, our Faraday's second law, rate of change, the derivative which will give you NAB, all constants being out of the operator. Now this cos omega giving rise to sin omega t. Sin omega t, of course that negative sign and always speaks of phase relation between the two terms, and again omega t derivative becomes one more omega. Therefore here you write it as E is equal to this NAB omega, all constant, because for a given coil number of turns, the cross section, the external induction that is being used and the velocity with which it is rotated in the magnetic field. All these are constant terms times sine omega t, and this is what is the famous alternating current. E is equal to E naught sine omega t. An AC voltage signal it is referred as. Because in this case, one rotation of the coil we can have 4 quarters, and in those 4 quarters the orientation of A bar with the flux changing all the time. Therefore, according to Lenz law, there what we find is the waveform. If I represent this waveform, see, time versus E. In this case, whatever EMF that is generated, it is not a steady one, both in terms of magnitude and also in terms of direction. Why direction sense is getting reversed? Because you remember phi is equal to NAB cos theta, theta is equal to 0 and theta becoming pi, then the sign getting changed, reversed, the negative becoming positive for a very pi value, negative becoming positive or positive becoming negative. So because of the change of orientation, we will have a signal like this. That is why it is called an AC signal, right? This is what we got. This being called as the positive half cycle, and this is called as negative half cycle. So this is 0 to capital T. One cycle I have shown. To show you in a much bigger way, only one cycle I will show you, because this also happens to be an important question. It can be. See, we are showing this as the positive half cycle and negative half cycle. 0 and this cycle at T ends, therefore this becomes T by 2, and these are symmetric. I write it as T by 4, 3T by 4. Now what you observe is that for every T by 2, the direction of induced EMF is getting reversed. For every t by 2, what you observe? That EMF starts from 0 and again becomes 0. 0 to 0 it happens, or has peak to peak also. See, this is t by 4 and this is 3t by 4. At these instants, what we see is that the voltage is peak. Therefore, 0 to 0, otherwise peak to peak. All such cases, the time interval, you will find it as t by 2. And this reversal of the direction is due to the reversal of the orientation. So this is a very popular topic. Remember, it's a very simple case of substitution, that's it. Given numbers, multiplication, get the answer. Now, this is what is the topic of electromagnetic induction. We could have used one more session for this, but almost all the topics we have covered with concepts and with numericals as well, and few things are left over, such as eddy currents or some other simple things, which you can just follow your notebook. Don't forget about your assignments. Again, I'm telling you, the most important session for you is this all time of tough corona times, staying at home, always with out of moods. Many of the students will be of that nature. Now, the one who makes the best use of this time definitely will be a winner. And I wish all my students to be winners. Make use of your time, do assignments. For any of the doubts, call your teachers. Have a good day.